Hello students, welcome to my YouTube channel Dear Mathematics, and also welcome to the chapter of permutation and combination. In the previous topic we have already discussed about factorials and some problems based upon factorials, then types of arrangements and problems based upon types of arrangements, and we have seen 4 types of arrangements there, and also we have solved some of the problems based upon the particular types of arrangements. In this particular session we are going to discuss about the topic of permutation. So before going to the topic of permutation, the formulas of permutation, let us discuss about the formula, or let us discuss about the definition of the permutation. Each of the different arrangements which can be made by taking some or all of a given number of things or objects at a single time is called as a permutation. And in this permutation topic, a vital term is here, and that is order of appearance. In permutation, order of appearance of things is taken into account. That means order of appearance must be there in the topic of permutation. So what do you mean by order of appearances? Suppose we have taken 2 digits, the first one is 1 and the second one is 3. 2 digits are there. So how we can get the result by using order of appearance, or we can say that how we can get the permutation or total number of arrangements by using the order of appearance. Suppose we have to form 2-digit numbers by using the distinct digits 1 and 3. The unit place, suppose it is filled up by 3 and the 10th place is filled up by 1. Then the number we are getting here, that is 13. Suppose in another way the order has been changed. Suppose the interchanging the order, or you can say that interchanging or changing the position of the 2 digits 1 and 3. That means the unit place is filled up by 1 and the 10th place is filled up by 3. Then here we are getting a 2-digit number, and that is 31. And you already know that 13 is not equal to 31. That means we cannot write down 13. We have to write down 13 as well as we have to write down 31. That means two-digit numbers we can get by using the 2 distinct digits 1 and 3. So order of appearance is most important here. So let us discuss about something more about the order of appearance. Then we have to proceed towards the theorems. So to describe the order of appearance in the problem manners, so we have taken an example here. Consider the 3 letters A, B and C. We have to form 2-lettered words. The following 6 arrangements can be made with the 3 distinct objects, or you can say that 3 distinct letters, taking 2 at a time. And these are A, B, B, A, B, C, C, B, A, C and C, A. 6 types of 2-lettered words can be formed by using the 3 letters A, B, C. Each of this arrangement is called a permutation. But the order of appearance really matters here. So what does mean by order of appearance here in this problem? AV is different. AV is different from BA. Similarly, BC is different from CB. Similarly, AC is different from CA. The word AV, the 2-lettered word AV is not equal to BA. Similarly, the word BC is different from CB. The word AC is different from the 2-lettered word CA. So this is the very simple example based upon the order of appearance and to solve a permutation problem. Then moving towards to the notation of a permutation. If n and r are positive integers, 2 positive integers, such that 1 less than equal to r less than equal to n. N denotes the number of objects and r denotes the number of places, or you can say that the number of choosings. And then the number of all permutations of n distinct things taken are at a time, choosing, is denoted by PNR or n pair. The 2 types of notations are there. You can choose either of them. So P of NR is simply called as, or simply denotes, or simply tells total number of permutations, or you can say the total number of arrangements of n different things taken are at a time. So this is the notation to denote a permutation of a total number of objects and then choosing some of the elements or all of the elements. Then moving towards to the first theorem, very important theorem of permutation topic. So here it is the theorem number 1. Let r and n be two positive integers such that 1 less than equal to r less than equal to n, and we have already discussed it. Then the number of all permutations of n distinct things taken r at a time is given by, it is denoted by p of nr or npr. We have already discussed it little while ago in the notation part. Then it is defined as the multiplication of n with n minus 1 with n minus 2 with the last term n minus r plus 1. Here, the number of permutations of n distinct things taken r at a time is very much equal to the number of ways in which we can fill up the r places by using the given n number of digits. That means, first of all, let us consider or let us take the r places here and n objects here, and we have to fill up the r places. This is the first place, this is the second place. This is the second place, this is the third place, this is the rth place. As 1 is less than equal to r, less than equal to n, that means n is greater than r. Here we have to consider r as less than n. Here we have to consider r is less than n. So the first place can be filled up by n number of ways. As we have to use the distinct digits, the second place can be filled up by n minus 1, 1 less than the first place, that means n minus 1. Then again one object is filled up here, the remaining objects are there, n minus 2. So the third place can be filled up by n minus 2 number of ways. Let us convert this data into another form, and we have to express them according to their position. Suppose we have to express n in terms of 1. So how we can express? N can be expressed as n minus 1 minus 1. 1 minus 1 is 0, n minus 0 is equal to n. Then we have to express this n minus 1, and we can express this like n minus 2 minus 1, and we have to express according to their position. And you can see that here it is 2 and the position is 2. Then we have to express this third place or n minus 2 in terms of their position. So it can be expressed as n minus 3 minus 1. 3 minus 1 it is 2, n minus 2 is here. Similarly, as first position can be filled up by n minus 1 minus 1. Second position can be filled up by n minus 2 minus 1. Third place can be filled up by n minus 3 minus 1. Similarly, the rth place can be filled up by n minus r minus 1. So this is the need of this conversion. We have to find out the total number of possibilities to fill up the rth place, the last place. Just taking or simplifying this, we have n minus r plus 1, and we require this term n minus r plus 1 to evaluate this value. So first place can be filled up by n number of ways. N number of ways. Second place can be filled up by n minus 1 number of ways. Third place can be filled up by n minus 2 number of ways. Similarly, rth place can be filled up by, we have already evaluated it, it is n minus r plus 1 number of ways. So by using the counting principle of multiplication here, the total number of permutations or you can say that arrangements is equal to n multiplied with n minus 1. Okay, let us write down the total number of permutations of n distinct things, taken r at a time, is given by PNR or NPR. We have to use the counting principle of multiplication here. N multiplied with n minus 1 multiplied with n minus 2 n minus r plus 1. You can also write down here, in place of n minus r plus 1, you can also write down n minus r minus 1. You can also write down in place of this. Okay, so this is the proof of the first theorem based upon the topic permutation. Then moving towards to the next theorem. Here it is the theorem number 2, and here we have to prove that the permutation of n number of distinct things taken r at a time, it is equal to n factorial divided by factorial of n minus r. So you have to prove this by using the theorem number 1. But before going to the proof, let us consider again the term factorial here. We know that n factorial can be written as 1 multiplied with 2 multiplied with 3 multiplied with n minus 1 multiplied with n. And also we can also write down in the reverse order, n multiplied with n minus 1 multiplied with n minus 2 1. You can write down it is in the increasing order, and this is the decreasing order arrangement of the factorial of n. And we have to use it, this decreasing order. That means we have to multiply the continued product. We have to find out the continued product of n number of objects starting from 1 up to that number. So from theorem number 1, we have P and R is equal to n multiplied with n minus 1 multiplied with n minus 2 n minus r plus 1. Here it is a continued product. This is a continued product, and this is in the decreasing order. N, then the previous term n minus 1, then its previous term n minus 2, up to n minus r plus 1. But this is not continued until the term 1 here. That means we have to continue this product up to that reaches up to 1. So n multiplied with n minus 1 multiplied with n minus 2 n minus r plus 1. Then we have to multiply its previous term, that means n minus r. Then its previous term n minus r minus 1 up to 1. That means we have multiplied n minus r minus 1 up to 1. And then again we have to multiply those terms in the denominator again. That means n minus r minus 1 is equal to 1. You can see that now the numerator is in such a form that this is the continued product of n different things or n different numbers starting from 1 up to n. That means it is none other than n factorial. Again, the denominator is in such a form, it is again in the decreasing order. It is the continued product, and it has been started from 1 up to n minus r. That means it is the factorial of n minus r. So the very shortcut formula of the permutation of n different things taken r at a time is given by n factorial divided by factorial of n minus r. So this is all about the theorem number 2. You can also prove some of the examples. Suppose we have to find out P63. Then it is 6 factorial divided by 6 minus 3 factorial, 6 minus 3 factorial. Then 6 factorial divided by 3 factorial. You can also convert this 6 factorial in terms of 3 factorial, 4, 5 and 6. Just cancelling, you can have your answer, and this is 120. So this is a short bit question based upon the theorem number 2. Then let us move towards to the theorem number 3. So here it is the theorem number 3, and here we have to prove that the number of all permutations of n distinct things taken all at a time is n factorial. That means in this problem the value of r and n are equal with each other. Before going to the proof of the theorem number 3, let us discuss about some of the fundamentals. Suppose we have given 3 number of objects, and also we have given r is equal to 3. R as 3. That means 3 places are there. Number of places is equal to 3, and also the number of objects is equal to 3. That means here n is equal to r. That means the number of all permutations of 3 distinct things taken 3 at a time, taken all at a time. So the first place, as we have to use the distinct things, that means the repetition is not allowed here. The first place can be filled up by 3 number of ways. The second place can be filled up by 2 number of ways. So for the last place there will be a single element. That means it will be arranged or it will be filled up by only 1 number of ways. So in this type of a problem where n is equal to r, then for the last place there will be a single element. That means if n is equal to r, then first place can be filled up by 3 number of ways, the second place can be filled up by 2 number of ways, and the last place, or you can say the third place, can be filled up by 1 number of ways. Similarly, in this theorem number 3, there are n number of objects and also n number of places. The first place, this is the first place, this is the second place, this is the third place, and here rth is equal to nth place. First place can be filled up by n number of ways. Second place can be filled up by n minus 1 number of ways. Third place can be filled up by n minus 2 number of ways. As I have already told, if n is equal to r, then for the last place there will be a single element to fill up this place. That means the last place or the nth place can be filled up by 1 number of ways. Let us write down the proof here. First place can be filled up by n number of ways, n number of ways. Second place can be filled up by n minus 1 number of ways. Third place can be filled up by n minus 2 number of ways. Similarly, the last place can be filled up by 1 number of ways. 1 number of ways, because I have already told that for the last place there will be only a single element there. So the total number of permutations, hence the total number of permutations of n distinct things taken all at a time is Pnn. In place of r, we have to write down n, because here n is equal to r. So by using the counting principle of multiplication, it is n multiplied with n minus 1 multiplied with n minus 2 1. So P of n, permutation of n different things taken n at a time or all at a time, is equal to n factorial, and this is the proof of the theorem number 3. Then moving towards to the theorem number 4. Theorem number 4 tells that here we have to prove that 0 factorial is equal to 1, because in the very first topic of a factorial The beginning topic of chapter permutation and combination, I have already told that 0 factorial is equal to 1 and we have to prove it later part in the permutation topic. So here it is the time for to prove the value of a 0 factorial is equal to 1. From theorem number 3, we have permutation of n different things taken all at a time is equal to n factorial. Then applying theorem number 2, n factorial divided by factorial of n minus n is equal to n factorial. What does tell the theorem number 2? Permutation of n different things taken r at a time is equal to n factorial divided by factorial of n minus r. So by applying this theorem here, n factorial divided by 0 factorial is equal to n factorial. Just changing the side of 0 factorial and the right hand side n factorial. Here we have n factorial divided by n factorial is equal to 0 factorial. Just cancelling both of the numerator and denominator, we have 0 factorial is equal to 1, and here it is the proof of the theorem number 4, and it is very important for the exam point of view. Then moving towards some of the notes that are based upon this theorem, theorem 1, theorem 2, theorem 3 and theorem 4. That is the first note, or you can say that the first corollary which is based upon the theorem number 2. And here we have to show that the number of permutations of n different things taken are at a time where repetition is allowed is equal to n to the power r. That means the first condition is r less than n, and you have to understand that because two types of integers are given to you, one is n and another is r, and relation between n and r less than equal to n, and you have to consider r less than n here in this note number 1, and in the note number 2 you have to consider n is equal to r. So there are r number of places and n number of objects here. The first place can be filled up by n number of ways. The second place can be filled up by n number of ways again because repetition is allowed. Then the third place can be filled up by again n number of ways. Similarly, the rth place can be filled up by n number of ways. So the multiplication of n r times is equal to n to the power r, and this is very simple proof for the first corollary. So first place can be filled up by n number of ways. Second place can be filled up by n number of ways. Third place can be filled up by n number of ways. Similarly, rth place can be filled up by n number of ways. So the total permutations, total number of permutations of n distinct things taken r at a time where repetition is allowed or is given by n multiplied with n dot n r times. Hence the result is n to the power r, and this is the proof of the first corollary which is based upon theorem number 2. So here it is the last part of this current video session, permutation topic, and here we have to show that the number of permutations of n different things taken all at a time where repetition is allowed is equal to n to the power n. So there are n number of objects as well as n number of places, and here n is equal to r. But here repetition is allowed. Repetition of objects, or you can say that things, repetition of things is allowed. So the first place can be filled up by n number of s, second place can be filled up by n number of s, third place can be filled up by n number of s. Similarly, the last place, this is the last place, or you can say that nth place, again it can be filled up by n number of s because repetition is allowed. Otherwise, if n is not equal to r, it will be different. So here the number of permutations is equal to n multiplied with n multiplied with n multiplied with n times, because n is equal to r and it is equal to n to the power n. Let us write down the proof here. First place can be filled up by n number of which second place can be filled up by n number of which third place can be filled up by n number of which. Similarly, the nth place can be filled up by n number of which. Hence, the total number of permutations, the total number of permutations of n different things, taken all at a time, is given by, here repetition is allowed, is given by n multiplied with n multiplied with n multiplied with to n, and here it is n times. That means the resultant is n to the power n, and here it has been proved. So in this particular topic, we have discussed about, or we have just started the topic of permutation, and we have seen the definition, then it's the notation, then it's the order of appearance, then we have seen the 4 different important theorems and some of the basic corollaries based upon the theorems. In the next topic, we will see again the permutation topic.